Okay, so this will probably be the last lecture example of the course, and to see finally how we include rotational kinetic energy into the law of conservation of energy. So law of conservation of energy together. Okay, so we're gonna ask the question of if we have a slope like this, and if I put a ball, a sphere, and have mass m and roll down, okay, what is the final speed? All right, so what's the final speed it arrives over here? Well, if we treat it as a point mass, so if it's just like a point of mass m, let's say little m, it doesn't rotate. So if it's a point, it cannot rotate. So what's the quickest way to find the speed? It arrives over here. It's by conservation of energy, right? So let's say I'm given, let's use the actual variables given. I'm given the height. Okay, so vertical distance is y, and little m I am given, h, this is the height of it. And I think that is, oh yeah, that's all I need, right? So, so what's the initial energy at first? So we're gonna do energy initial equals to energy final, right? Initially, it release at rest, everything. So at first, it's just mgh, little m g capital H, it should equals to 1/2 little m v squared, right? Yeah, let's call this capital V, okay, for the big ball. So we differentiate them, right? So little v is very easy. It's just the m's cancel, right? So 2gh square root. I'm talking about speed, so I'll choose the positive square root, right? So keep that in mind. For this, the answer is 2gh. Now, what if I have a sphere? So this time, what's the difference is this guy will rotate, okay? So if it rotates, so now we need to do a little bit more in the final case. We need to add in the rotational kinetic energy. So at first you need to add, so what other energies are there? So there is translational kinetic energy, rotational kinetic energy, and gravitational potential energy, right? So all of them, look at the initial and look at the final. Translational final plus rotational final plus potential energy final, all right? At first, it's released at rest, so there's no translational kinetic energy. It's not rotating at first, so there's nothing. So we just have mgh. Okay. Which m? Capital M, which h? Say same height. Okay. And so we have this. But this, at the end, we don't have this, but we are gonna be rotating and moving linearly as well. So we have 1/2 capital M capital V squared plus the rotation is 1/2 I of the sphere and the omega of the sphere, right? What am I interested in? I'm interested in this. However, I need to rewrite these. These two are symbols I just created that is not given in the problem, right? I'm just given M, H, and V, right? So I need to find out what that is, but I will look up the sphere is 2/5 of mr squared. So this is the radius. I must need the radius of that guy as well at some point, I think. Little r, is that what's given? Yeah, maybe they cancel out, we'll see. Yeah, so that's r0, let's call that, right? So in my case, this is r0 squared, all right? So well, what do we have? So 1/2 mv squared plus 1/2 2/5 capital M r0 squared, okay? What's omega of the sphere? Well, yeah, so what's the angular speed? I don't know, but I can relate it to the linear one, where it's related this way, right? So I can write omega as V, capital V over r0, right? All things squared. The r0 does cancel, so that's nice. What does that tell you, right? So the whole thing, once I solve for V, I can sort of see in advance that the r0's not gonna bother me anymore, right? So this is actually independent on R naught. It's quite interesting, right? So when you, the speed over here, that when you get to the bottom, it's independent on the radius of that. It just depends on the fact that it does spin, okay? All right, so we will simplify this mess. So mv squared plus 1/2 and 2/5, so this is 1/5 m, and then the R naught square cancel, just have v squared, which gives me, there we go, 1/2 plus 1/5 mv squared. So so this is 5/10, this is 2/10, right, essentially. So I essentially have 5/10 here, and we have 2/10 here, mv squared. So this would be 7/10. So on the left, we have mgh, that's the initial total energy. This time we included the rotational contribution. And we have on the right, 7/10 mv squared. M's cancel, what's v? So v is now 10/7 gh square root. Okay. Can you see the difference whether when things rotate or not? If it does not rotate, that's it. If it does rotate, this is it. Which one's larger? Well, what's 10/7? Let's compare that, right? 10/7 is 1 and 3/7. Okay, so yeah, right. So that's 1 plus 3/7. Right? There, and 3/7 is I think is 0.4827. I think you can double check that. So 10/7 should be 1.4827, I believe. We'll just double check that in case I need to correct that later. So yeah, close enough. 2/8. There we go. Just in case. There we go. All right. So here I have 1.428 GH. So which one is larger? This one is larger, right? So why does that happen? So this guy is larger speed over here is because part of the energy, they started off with the same at the same heights, right? So there's the same amount of, technically this has more potential energy because of capital M, but as you can see, the M cancels out and it doesn't affect the speed. So yeah, they have the same height. So they have, let's assume they have the same mass, then this guy, they have the same potential energy, but part of it here, all of the potential energy goes to moving it forward. Here, part of the energy goes to moving forward, part of the energy goes to overcoming it and making it rotate. There's inertia to overcome linear motion, there's inertia to overcome rotational. So you see there's more, so part of this is translated to both of these, and it's less. So in fact, a better comparison will look at how much faster this is to this. So let's look at little v over capital V. So we have 2gh over 10/7 gh, right? So now the gh cancels, square root of the 7 goes on top, so 14/10. So that's basically square root of 1.4. So it's around that factor. Is that roughly 1.2? Yeah, we'll double check that. But so it's not that much when you realize the little v is 1.2 times faster than capital V. So around 20% faster. Okay, so yeah, I think this will set you up. You can look through all the other examples in the textbook, and you can see all the different variations, but you see the concepts are very translatable. We spent a little bit more time in looking at all the basics. So just to wrap up, right, we spent a lot of time looking at basics. We went a little bit fast with the rotational stuff. However, I think that's okay because part of what I see myself, it is impossible within 5 weeks to cover of the summer session to cover everything in very, very excruciating detail. So it's really a balance of me going through, should I just throw you a bunch of knowledge to memorize through the whole course? Or should I, some parts go slower and make you really understand the stuff? So you have a good foundation that you guys are all smart students. The fact that you are taking this course in this university, very prestigious university, you have you have a certain amount of abilities, right? So I'll set you up with the basics, and you'll be able to take those basics and learn from yourself. In some sense, also, you will see my rationale of speeding up a little bit at the back is these things, the rotational stuff is important to complete the journey of asking the questions of why things move and how to analyze motion. This is basically our central theme, but it doesn't affect too much with 3B and 3C, okay? Whereas everything in the first 4 weeks are very fundamental to other things. You will have a little bit of rotational stuff, but not that much. When you see, even though the rotational stuff is a lot of new information, but they're based on a lot of old information, all right? So hopefully you'll have a lot, you've taken a lot of value out of this course, and the rest is really look through, read the textbook yourself. Hopefully my job has completed in the sense of preparing you with a good foundation. It's like after you watch the movie, you want to read the book. So now you've watched the movie, you want to, hopefully my job has been achieved in making your reading much more easier in that way. All right, so we will do a little review and we'll see what we can put together, help you consolidate everything, either with more examples or just a key summary of some of the key concepts from this very, very vast course. Okay, in any case, all the best, and yeah, good luck with your studies. I'll see you soon.